OCR Chemistry A, carbon-carbon bond formation. Getting the most from Chemistry Explained means taking notes and completing tasks on paper or on a tablet, controlling the pace at which the lesson proceeds. Particularly when prompted, pause the lesson, complete the task, thinking it through, taking your time. When you're ready, return to the lesson and correct your work before proceeding. We'll start with carbon chain extension and look at the reactions of the cyanides that achieve that, and then the reactions of the nitriles that are formed by the cyanide reactions, and then we'll review aromatic Friedel-Crafts reactions. Do feel free to skip ahead to any of those sections. There are only a few reactions that extend the carbon chain, and they all of course involve the formation of a carbon-carbon bond. If you've been following the OCR Chemistry A course, then you will have met the following reactions. The reaction of the cyanide ion with haloalkanes, the reaction of the cyanide ion or hydrogen cyanide with carbonyls, the reactions of haloalkanes in the presence of a halogen carrier with the benzene ring, and the reaction of acyl chlorides in the presence of a halogen carrier with the benzene ring. So we will review all of those carbon-carbon bond forming reactions in this lesson. But before we proceed, I just want to make it absolutely clear what we are concerned with here. It's the extension of the carbon chain or ring, which is a crucial step in synthetic pathways, moving from the starting materials that are available to a target or desired organic molecule. So let's just look at a couple of examples just to illustrate the points. Bromoethane is a common starting material, and we go to propan-1-ol. So bromoethane, missing out the hydrogens if you'll allow, there's bromoethane. Propan-1-ol, well, we've got 3 carbons in propan-1-ol, but only 2 in bromoethane. We've had to make an additional carbon-carbon bond. In an aromatic context, we might start with phenol, we might move to 2-hydroxybenzoic acid. So our starting material would be phenol, our target molecule 2-hydroxybenzoic acid, so again we have formed a carbon-carbon bond to extend the carbon chain. So earlier in the course you will have met 2 reactions of the cyanide ion, both of which result in a carbon-carbon bond formation, and we are going to review both of those. So haloalkanes react with cyanide ions to form organic nitriles in a nucleophilic substitution, and we will take the opportunity to review the mechanism of nucleophilic substitution in the next few slides. So haloalkane, cyanide ion, gives us our nitrile and a halide ion. So it's a substitution. The halide ion leaves and the cyanide ion is substituted into the organic molecule. So let's look at an example. So here's bromoethane and the cyanide ion. It's a simple exercise. Pause the lesson and complete the reaction equation. Come back when you are ready. Okay, so there is the bromide ion that has left, and the cyanide ion has been substituted in. Now we call the molecule on the right here propane nitrile. The carbon of the nitrile group is included in the carbon chain, so it's a carbon chain of 3. So we go from bromoethane with 2 carbons to propane nitrile with 3. You may see the equation written not as an ionic equation, but involving potassium cyanide, which would be the reagent, and of course we just, instead of bromide ion, we get potassium bromide. You need to know the solvent. So the reagent would be potassium cyanide, I beg your pardon, potassium cyanide, and the solvent would be ethanol. So you are expected to recall the solvent and the reagent for that reaction. Let's look at the mechanism for nucleophilic substitution. So first of all, you might just pause and recall a description of a nucleophile. Okay, so a nucleophile is an electron pair donor, and in donating a pair of electrons, a covalent bond is formed. So we are going to look at the nucleophilic substitution involving primary haloalkanes. You may find on other specifications secondary and tertiary haloalkanes are included. It's not the case in Chemistry A. OCR Chemistry A only requires the mechanism for the nucleophilic substitution reactions of primary haloalkanes. And of course we need a cyanide ion. Pause, add in the necessary bond polarities and 2 curly arrows for the first steps in the mechanism. Come back to check against my suggestions. Okay, so if we're going to form the nitrile with the bromide ion being leaving, then we need to have bond polarities which allow for the donation of an electron pair. So carbon delta plus, bromine is more electronegative, so bromine delta minus. And we have a lone pair of electrons on the carbon attacking the electron deficient carbon, the delta plus carbon, and that causes a movement of electrons from the carbon-bromine bond, which is already polarized, onto the bromine. So the pair of electrons that are in this bond appear here as a lone pair. The pair of electrons here, the lone pair here, appear in the final product as the carbon-carbon bond that has been formed. So here's a problem. Show the nucleophilic substitution mechanism for the formation of butane nitrile from a suitable bromoalkane. So you must decide on the reactant. Pause and come back when you have drawn out your mechanism with bond polarities, curly arrows, and the equation properly balanced. Okay, I'm about to reveal. There is the butane nitrile, if you weren't clear. Butane nitrile, of course, 1, 2, 3, 4 carbons. The carbon of the nitrile group is included in the carbon chain, so it's butane nitrile. So we're going to start with 3 carbons, so 1 bromopropane. We need a cyanide ion, of course, with a lone pair of electrons highlighted. We need the bond polarities to explain this movement of electrons donated to the electron deficient carbon, and the electrons in the carbon-bromine bond repelled by that movement of electrons onto the carbon deficient, the electron deficient carbon, repelled onto the bromine. So we must balance with the bromide ion. Don't forget the bromide ion. So many students, having marked lots of exams over the years, so many students get the whole idea correct but forget to balance. Ideally, you'd have the lone pair of electrons being highlighted there as well. So the second reaction of the cyanide ion that you will have met is the reaction with carbonyls, and we usually present it as a reaction of the carbonyl with hydrogen cyanide, forming a 2-hydroxynitrile in a nucleophilic addition. We will review the mechanism in due course. So let's look at the first type of carbonyl, the aldehyde. Of course, there are 2 types of carbonyl on our specification, aldehyde and ketone. Reacting with the hydrogen cyanide, that will produce a 2-hydroxynitrile. So let's look at an example. Simple aldehyde, ethanal, reacting with hydrogen cyanide. Would you like to write out the structure and perhaps draw a displayed diagram? Pause and come back when you are ready. So the structure, CH3CHOHCN, and what would that look like as a displayed structure? Well, let's have a go over here. So CH3, carbon, bonded to the hydroxyl group of our hydroxynitrile and the nitrile group of the hydroxynitrile. In terms of numbering, just so that we understand why it's a 2-hydroxynitrile, this becomes carbon number 1. So this is carbon number 2, this will be carbon number 3. So the positioning is quite clear. The hydroxyl group is on the second carbon, so it's a 2-hydroxynitrile. Try the ketone. Simple ketone, simplest ketone, propanone, and hydrogen cyanide. Predict the product, which is actually a 2-hydroxynitrile. Draw the structure and perhaps a displayed diagram to reinforce your understanding. Pause, come back when you are ready. Okay, so if I reveal, there is our structure. So what does that look like in displayed terms? Well, CH3, COH, CN, CH3. Again, it is a 2-hydroxynitrile, carbon number 1, carbon number 2, carbon number 3. So it would be 2-methyl, 2-hydroxypropane nitrile. However, it is a 2-hydroxynitrile because the hydroxyl group is on the second carbon. Looking at the reaction mechanism, the nucleophilic addition, let's start with a simple aldehyde, ethanal. And the first point to make is one that you should make in an exam, is that hydrogen cyanide, the reactant, is a weak acid and will dissociate to release hydrogen ions and cyanide ions in solution. We also, of course, need to explain why the electron pair moves at all, and that's due to the bond polarity. Oxygen is more electronegative than carbon, so delta minus delta plus. So let's bring in the cyanide ion. This pair of electrons will move into the electron deficient carbon, carbon delta plus, and those will repel the electrons that are already polarized towards the oxygen onto the oxygen. Could you pause and draw the intermediate that is formed? Draw the intermediate structure that is formed. Okay, I'm going to reveal. So there is the intermediate structure. What's happened is this pair of electrons here is now forming this covalent bond. So we've formed a carbon-carbon bond, which is our topic of our lesson. The oxygen here now has a lone pair of electrons which needs to be marked in. And it used to have a share of a pair of electrons in the bond. It now has both of the electrons positioned on it as an atom, so it's got a negative charge. Now we need to now also bring in the hydrogen ion here, because we're going to move electrons from the oxygen as a pair to form a bond between the oxygen and the hydrogen. So we need to place our arrow starting at the lone pair of electrons. So starting at the lone pair of electrons, it must be at the lone pair of electrons, and ending, the arrowhead ending, where we're going to draw the covalent bond between oxygen and hydrogen. So if we look at the end product, we'll see that this pair of electrons, this lone pair, is now constituting this oxygen-hydrogen covalent bond. It is now a shared pair. And there is our hydroxynitrile product. So here's a problem for you. Imagine you are asked to write the mechanism for the nucleophilic addition of hydrogen cyanide to a ketone propanone. Pause, complete the mechanism in all its detail, and come back to compare to my own. Okay, I'm about to reveal. So of course the first thing, as I mentioned on the last slide, is to highlight the fact that the hydrogen cyanide is a weak acid and releases H+ and cyanide ions. We need the bond polarities. We need the cyanide ion. Of course, we need to add in the movement of electron pairs with a curly arrow, 1 and 2. We need to then produce our intermediate with our lone pair of electrons, which is going to move to form the covalent bond between the oxygen and the hydrogen. So you would normally be looking like, if we were marking this, be looking like probably 1 mark for both curly arrows, 1 mark for the structure, 1 mark for that movement of the lone pair of electrons on the oxygen to form the bond. And if you are lucky or asked to do so, you might get a 4th mark for the hydrogen cyanide part. The usefulness of forming nitriles is in their further reaction. So there are 2 further reactions of nitriles that you are expected to know about. So the first issue about the reactions of the nitriles is to know them factually. So the first one is the hydrolysis of the nitrile to form a carboxylic acid. You need to know the conditions. Dilute aqueous acid, for instance, dilute hydrochloric acid, and it needs to be heated. So we might change propane nitrile, for instance, into propanoic acid. So having made propane nitrile, propanoic acid can then be made from the nitrile. So if we look at the equation, there is propane nitrile, there's some water, there's HCl from the hydrochloric acid. Pause and complete the equation. Come back when you are ready to check your answer. Okay, so there are the products: propanoic acid and ammonium chloride. A Point out there are 2 oxygens in propanoic acid. There's only 1 oxygen at the moment on the left hand side in the reactants, so you need to balance that with 2 H2O. It's a very common oversight, a relatively straightforward mark lost through incorrect balancing, so please make sure you balance your equations. So there is propane nitrile turned into propanoic acid. Now the advantage of making propanoic acid is that from propanoic acid, a carboxylic acid, an ester can be formed, or we could reduce it to an alcohol. From an alcohol, we've got access to alkenes, we've got access to haloalkanes, we've got access to carbonyls such as aldehydes and ketones. So the conversion of the propane nitrile into propanoic acid is a very important step in synthetic pathways. Now the second reaction of nitriles, the reduction to form amines, is not as versatile or useful in synthetic pathways. Nevertheless, it has its uses. So the conditions, again, you are expected to know: hydrogen gas with a hot nickel catalyst. Now that's exactly like the reaction of alkenes to form alkanes. So hydrogen gas, hot nickel catalyst. Let's have a look at an equation to express propane nitrile to form propyl amine. So there is propane nitrile, there is the balanced number of hydrogens. Can you pause and complete with the correct product? Okay, I'm going to reveal. Don't pause again if you're not ready, but if you are, here is the correct answer. So we have propyl amine. We've added 2 hydrogens to the carbon of the nitrile and 2 carbons to the nitrogen of the nitrile. So I may remind you, there's initially a triple bond in the nitrile group, carbon triple bond nitrogen. So it's now carbon single bond nitrogen, CH2 NH2. So there is our propyl amine product. Moving on to Friedel-Crafts reactions, which is the formation of carbon-carbon bonds in the context of benzene chemistry. Moving on to the Friedel-Crafts, our first one you may recall is alkylation, which involves a benzene and a haloalkane. So a very simple substitution pattern. One of the hydrogens from the benzene ring leaves and forms hydrogen chloride with the chlorine from the haloalkane, and the methyl ethyl, the alkyl group, is substituted into the benzene ring. You do not need to know the mechanism for that reaction in Chemistry A, OCR Chemistry A. However, the pattern of that substitution is expected to be known. So let's look at an example. Benzene and chloromethane. Pause, draw the structure of the products. Come back when you are ready to compare to mine. Okay, so revealing, here is the product, methylbenzene, and here is the other product, hydrogen chloride. So it's always following the same pattern. We've taken a hydrogen from the benzene ring here, and that's it originates and ends up in hydrogen chloride, and the methyl group in this instance is substituted into the benzene ring to make methylbenzene. We need a catalyst, a halogen carrier, as mentioned earlier in the lesson. Well, that's going to be more or less the similarity with halogenation is what you're drawing upon here. The mechanism is very similar to halogenation, so we need a catalyst, iron 3 chloride, to act as halogen carrier. So moving on to Friedel-Crafts acylation. So here, rather than a haloalkane, we have an acyl chloride. Again, the pattern is we form hydrogen chloride or the hydrogen halide, but instead of the alkyl group, we've got the acyl group, RC double bond O, R carbon double bond oxygen, substituting into the benzene ring. So if we look at the structure of our acyl chloride, and a simple one such as ethanoyl chloride, we have a catalyst of iron 3 chloride, a halogen carrier, just as with halogenation. Could you pause and predict the product of this substitution reaction? Come back when you are ready to check your answer. So I'm about to reveal. So the chlorine in the acyl chloride ends up in the hydrogen chloride. A hydrogen from the benzene ring leaves and contributes to the hydrogen chloride. The carbon of the acyl or carbonyl group forms a carbon-carbon bond with the carbon of the benzene ring. So this is the topic of our lesson. We've formed a carbon-carbon bond here. Of course, the catalyst or the halogen carrier is, for instance, iron 3 chloride. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.